Okay, so I'm just recording. All right. So we'll begin. Module 12 review. All right. And as I said, the topics covered, these are come from chapter 16, 2 tests. One is called the goodness of fit test, and the other one is called the test of independence. So what we're looking at in this chapter for these two sections is categorical data. So data that is organized in categories. So we call it count data because we just count the number of observations that have that characteristic or that in that category. These tests come from a family of tests called the chi-square. So the chi-square tests are a family of tests, and these are two tests that come from that family. So they both use chi-square, and we'll look at two examples. So goodness of fit. Let's look at the formula first, because we should know what the formula is, and then we'll talk about what goodness of fit means with an example. So there's our chi-square. We know that that's chi-square. Chi-square. And it's the sum, right? We know the sum, that's the sigma, the capital sigma. This is F subscript O, and the O means observed. The observed counts. So the notation of the textbook is F subscript O, but what it means is it's the frequency of the observed distribution. So we can also call it the observed counts. O for observed, and this one has a subscript E, and it's, so this is O for observed, this is E for expected counts. O and E, and the denominator is also the same value. You square the numerator, the difference, and then we use degrees of freedom because it's a chi-square distribution. This K is the number of categories. And there we have it. Sometimes this is shown in books. This is how I've seen it a lot, with observed, capital O as a variable, subtract the expected. So you might have seen it like this before too, or you might see it like this in other contexts. You square that and divide by the expected. So observed minus the expected, all squared, divide by the expected. You can think of it that way if you want. Instead of the F subscript O, it's a little bit more cluttered, but I like the O subtract E divided by E, but we'll stay with the textbook notation so that it's clear. But just know it's observed, subtract the expected, divided by the expected. Now, what are these observed and expected values? Well, let's look at an example. We'll see what they mean by observed and expected, and what does it mean by goodness of fit. So we have this categorical data, and it's showing the absenteeism for students. Now let's just set this up. So absenteeism of university students from math classes is a major concern to math instructors because missing class appears to increase the drop rate, and we know that. So suppose a study was done, and these studies are done, to determine if the actual study absenteeism rate follows faculty perception. So perception means what they would expect the distribution to look like. So the faculty expected that a group of 100 students would miss class according to this chart. So this is 0. So this is the number of absences per term in days. All right. You can hear me? Yep. So this is the number of absences per term in days. So 0 to 2 days. Hello, you're speaking? Yeah. Okay, good. All right, because I just was hearing someone speak, trying to speak, I think. Okay, so the expected number is what they would expect to see. So this is before they actually collected any data. This is the expected value. So the expected number of students per day. So they figured for 0 to 2 days, they would expect to see 50 students. And for 3 to 5 days absent, they figured they would expect to see 30 students out of 100. Remember, it's out of 100. And they figured that between 6 and 8 days, 12 students would be absent. And then 8 students would be absent, probably, they figured 9 or more days. And so this is what they thought would be reasonable and what they thought they would expect to see in the number of absences per term. Okay. And so I'm going to keep this. So this is the expected, these are the expected values, this column, and this is the categories, right? These are the categories, right? 0 to 2 days, 3 to 5 days, 6 to 8 days, 9 plus. So it's group data, if you remember way back from the beginning of the course, group data. So it's, we've grouped the counts, and I'm going to just copy this same table is going to be copied down to here, just so that we can look and compare to what actually happened. Okay, so remember, this was the expected. This was the expected number of students. And now this is what the data actually showed when they collected the data, and this is what actually happened. So we have keyword there, expected and actual. Another word for actual is observed. This is what they observed, right? And so what they saw was 35 students were absent 0 to 2 days. 40 students were absent 3 to 5 days. 20 students were absent 6 to 8 days, and 5 students were absent 9 or more days. So you can see that the distribution in the counts from what they expected to see and what they actually observed is different, right? There were a lot lower students that missed 0 to 2 days, 35 instead of 50. If you compare the 0 to 2 days categories, 3 to 5, they figured 30 out of 100 students, but there was actually 40. And then 12 between 6 and 8 days versus 20 students. And then there were less students missing 9 or more days, only 5 instead of what they thought would be 8. So we can see that there is a difference, but we want to know if the top distribution, so the expected number of students, that distribution has the same fit as the actual. So we want to see if there's a goodness of fit. What we're actually seeing, what we want to know is what was observed, the actual number of students. Does that distribution actually hold to the faculty perception? So we can write that down in words. There's no math with the null and alternative hypothesis. So the hypothesis is student absenteeism fits faculty perception. So this is what they expected. All right, and versus student. Now remember, we know how to do an alternative hypothesis. It's always a contradiction to the null. So it's just going to be student absenteeism does not fit. Right? Does not fit faculty perception. And we'll just test to see if the actual number of students distribution is the same as the expected. So that's where we get goodness of fit. We call it a goodness of fit. So how well does the actual fit the expected? So what we can do is we can look at each one We can look at each one. So, oops, let me grab this. So 0 to 2 days absent. We'll look at that category. So this is the category. Gory, if I can spell today, category. Okay, so we want that. And then we can go, well, I'm just going to, what would be the contribution to our chi-square formula? So the contribution to our chi-square formula, we know it's observed, subtract expected, all squared, divided by the expected. So for the first category, we want 35. That would be the observed. The expected would be 50. So we're just going to see what that contribution is. 35 subtract 50 squared. And then you always put in the expected in the denominator. So the contribution for that category, 0 to 2 days absent, is 4.5. We can then do the next category, 3 to 5 days absent. And we're going to get, well, we go up to our tables, and the observed is 40, but the expected was 30. So we'll find that contribution to the chi-square. 40, subtract 30, square it, divide by 30. I think you're going to see the pattern here. Next category was 6 to 8 days absent. And we'll go back up. We can see that it was observed as 20 and they expected 12. So 20 students subtract 12. Are you seeing the pattern here? It's going to be 5.333. And then finally, we want the 9 plus absent. 9 plus days absent. And what were they? 5 was observed. Expected was 8. So observed is 5, expected is 8. So you can see the pattern falling together here. 5 subtract 8 squared divided by 8 gives us 1.125. All right. So what we do is to get the chi-square value, it's quite simple now. We just add those up. 4.5 plus 3.333 plus 5.333 plus 1.125 and get 14.291. So that's the observed, right? We know that that's the observed chi-square. We know how to do the hypothesis test. You get the observed and you compare it to the critical value from the table. This one here for these tests, there's just a question here about, do we need to have for these tests, there is no math in the null and alternative hypothesis because we're dealing with categorical data. All the previous tests, the ones from assignment 5, you do need symbols for those. You need the math because it is dealing with quantitative data, not categorical data. So with quantitative data, like with everything from assignment 5, basically, I believe it was when we did the hypothesis test for the slope, for the regression, you needed to use math symbols, math notation. Okay, so with this, here's a poll. Let's try a poll. How many degrees of freedom then should we use for this question, for this example? You're welcome. So how many degrees of freedom are there for example 1? Now, we need to know that because we want to calculate, we want to get the table value so we can compare it to our observed chi-square. right, so lock in. Look at all those. Excellent. Good, good, good. Yes, you did. The assignment 5, if you came in late, assignment 5 was well done. I mentioned the average was 91%. So they were well done. It's a good, that hopefully is a good indication of how good the final exam will be. I believe the final exam will be, if that keeps up, that will be very good. Yeah, we use K because we want to distinguish it from the next example. Yeah, notation, you can use C if you want, if that helps you remember, but yeah, we're going to use C in the next example and you'll see why. All right, so I'm going to end the poll, lock in your answers, end the poll, and share the results. Majority knew and remembered what we had just discussed. Okay, how many categories do we have here? Well, we have 0 to 2 days, 3 to 5 days, 6 to 8 days, and 9 plus. So we have 4. 4 subtract 1 is going to give us 3 degrees of freedom, right? So let's use that. So I'm going to use that to get our chi-square. I'm going to put a star there because we all know what the star means. It's the critical value, the table value, and I'm going to use 0.05. Alpha equals 0.05 because it's what we use almost all the time, unless if something's not given, then you use alpha 0.05 or you use what's been given, but we'll go with 0.05. These tests, generally speaking, use alpha 0.05, and we want 3 degrees of freedom. So let's find that, and we'll compare it to what we calculated. So it's always going to be the upper tail. These chi-square tests are always the upper tail. So there's the alpha 0.05. That's the column you want to use most often. And there's 3 degrees of freedom because we had 4 categories. So we will use this 7.8147. Anybody disagree? All right. I'll stop sharing the results there. All right. So let's take that value back. 7.8147. Okay, we have to memorize that. Bring it back here. And that is 7.8147. So what we want to do is we want to compare this value with this value. And we always, for these tests, we always ask the question, is the chi-square greater than the chi-square observed? Because, and then I'll put a big question mark, because we're looking at the tail. We want to know if we are in the rejection region. If it is, if this is true, then we reject. So the chi-square is right here. This is the chi-square star. Is the observed, so 14.291, is it greater than 7.8147? And the answer is yes. Therefore, we reject our worded statement, written in words, the null hypothesis. So we would reject that student absenteeism fits the faculty perception. We're going to reject that, but we will accept the alternative. If you reject one, then you accept the other. So we can conclude that student absenteeism does not fit faculty perception. And that is called the chi-square goodness of fit test. These tests are done for self-reported absences. They'll be doing lots of analysis on that to see if, did the absenteeism really increase? They might use quantitative data. They might get the average number of SRAs, or they might use the counts and break it down into categories like this, into days. I'm not sure, but analysis have been done and will continue to be done on the self-reported absences because it's new. It started last year. So yeah, so this says it does not fit. So what does that really mean? Well, the faculty expected, a different distribution of absences per term. And what they observed is it's not the same. So they would probably then accept this distribution as being not fit. It does not fit what they expected, and then go forward with that analysis. Depends really what they're looking for and what they want to do. But they know it's not the same as what they expected to see. Right, so any questions on that? That's the one test. Does chi-square test, so there's a question here. Does chi-square test only can be one-sided? Yes, it's always just done exactly how we did it. The alpha test does not need to be divided. Nope. It's always done just like this. So it's nice. It's categorical data. It's the chi-square tests. There's a family of chi-square tests, and this is one of them. And it's done in words, null and alternative hypothesis. You just take your count data, take your expected, subtract, right? You just take the sum of your expected, subtract, or the sum of your observed, subtract the expected, divided by the expected. Just add those up, get your number, compare it to the table. It's always one-sided, and make a decision. And it's always the same question. Is the observed statistic, the chi-square statistic, greater than the critical value from the table? And it's done. So these tests are used a lot in class. Everyone ready to go on to the test of independence? This is another chi-square. We can see it right here from the formula. This, again, we have chi-square, chi-square. It's a chi-square statistic, and we should recognize the numerator. That's the observed counts. Observed counts with an O, subscript O. And we have our expected counts. And we'll see how this test is different than the one before. So here comes the C. Okay, so you were asking about why didn't we use C? We keep the K and separate for the goodness of fit test, and we use C here. So this will be what we're going to be analyzing here is categorical data. It's count data again, because we have observed counts and we have expected counts, O and E. And then we're going to look at it. The data is organized into a contingency table. So it's going to be a two-way table where we have two categorical variables, and we're going to see if there's a relationship between the two. We're testing if they are independent. If they are independent, then there's no relationship between the two. One does not depend on the other. And if we reject that they're independent, then we conclude that they're dependent, meaning there is a relationship. And so knowing one gives us information about the other. That's what that means. R is the number of rows. So that's the number of rows. And C is the number of columns. Because one categorical variable will be denoted in the rows, and then the other categorical variable will be the columns. And when you sum the rows, the sum of the rows is this value here, n subscript I, the total. And the sum of the columns is n subscript j. So when you take the sum of the columns, sum of the rows, multiply, should be a little multiply sign if you want to think of it that way. So you take the sum of the rows, multiply by the sum of the columns, or you can do it the other way, the sum of the total of the columns, multiply by the total of the rows for a specific cell, and then divide by the grand total. That's n. So let's look at an example. Everyone with me so far? This is our last example test of independence. So we're going to use this formula. So if you took Stats 1024, you might remember this. If you took it from me, you might remember this example. There was a in the United States, in one of the states, you could only purchase alcohol if you were under the age, if you were between 18 and 21. You could only purchase alcohol if you were female. Males were not allowed to purchase alcohol between that age, between 18 and 21. And so an 18-year-old male decided to challenge the state, took it to court. He got this roadside survey was conducted as part of his evidence, as well as they also looked at 3 months of tickets issued while driving under the influence. And they looked and they counted the number of males and the number of females that got those tickets. What we're going to do is we're going to look at his roadside survey. Coincidentally, it ended up going to the US Supreme Court and he won. And they changed the law. The law was changed forever. He won from this data set. So let's take a look and see what they did with the test of independence. What they wanted to do is they have two categorical variables. One is yes, no to a survey question. Have you drank alcohol in the last 2 hours? They were pulling people over from the roadside and asking them have you drank in the last 2 hours, yes or no, and doing the test to see if they had. And then gender was also recorded. So we have two categorical variables, the answer to the roadside survey, yes, no, and the gender, male, female. And the totals are there as well, right? The column, I put those in. Sometimes with these, this is a two-way table and because there's two categories. Sometimes the totals are not there. Sometimes you have to get the totals. You have to add the totals. So for example, there were 481 males in this study, right? That's the number of males. And there were 138 females in the study. Makes sense because more males, even today, more males drive than females, especially at night. And this was done at night. And then this is our capital N here. This is our total. There were 619 participants in this study. Again, this was just one part that allowed this male to win in the US Supreme Court. He had also another data set that showed the tickets that were issued, people who were actually charged while driving under the influence. This was just the survey. Have you had, one drink in the last 2 hours? Okay. And he won. So how did he win? So they presented this to the judge with a test of independence, because if they are independent, if you think about this, so the null hypothesis, if they are independent, then would he have won the case? Or if they are not independent, would he have won the case? So you think about that. You have to, so gender is one, right? And driving under the influence. Those are our two categories. Are independent. I'm going to try and squeeze that word in. Independent. Are independent. So that means there's no relationship between the two. Versus the alternative hypothesis is gender and driving under the influence. So they would have done this test. Are not independent, which means, i.e., they are dependent. So if I already have told you that the 18-year-old male won the case. He won the case, and because it was gender discrimination against males, and he fought it and won, and they changed the law so that they weren't discriminating between whether you were male or female onto whether you could purchase alcohol. So what do you think? Did they reject the null hypothesis, or did they not reject the null hypothesis? Because I already told you he won. So if there's a relationship, just think about it for a moment. If there's a relationship between gender and driving under the influence, then that means one cannot, yeah, probably did not reject. That means one, knowing gender can give you information about driving under the influence and vice versa. But if they're completely independent of each other, right, if gender and driving under the influence are independent, then one does not influence the other. And one knowing one does not give you information about the other. Right, so independent, think of them as almost being separated, independent of their own, where if they are not independent, then they're dependent, and that would mean that there is a relationship. So let's see how the test was calculated. We'll do the math here. So we just look at each category, right? There's males. Yes, so let's look at that category. And we need, though, to get the expected counts. So remember, the expected counts was the totals. If we go up to here, we need to do the expected counts are calculated by the row multiplied by the column totals divided by the grand total. So we need to do that first. That is going to be, so if we go for males, yes, so we'll look at it's, we can do the rows first if we want. 481 multiplied by total males that said yes is total people that said yes, I should say, is 93, divided by 619. So that's going to be the expected, 72.27. All right. Then what we do, we can get all the expected, or we can just, I'm going to just put down here. Now this will be the chi-square contribution. So this is going to be the f of 0, subtract the f of the expected, divided by the expected, right? We want that contribution. So now we can plug that in. So the number of males that said yes is 77. You can see that from the table. So it's going to be 77, subtract our expected value. These are the expected values. So 72, subtract 727, 72, yeah. Decimal 27 squared, 72.27 equals 0.310. So that's the contribution to the chi-square statistic for the males yes category. Let's go on to the males no category. And we want the expected. So the males no, so we know that there's 481 males, but the number of people who said no in this study was 526. Everyone see that? I can shrink that down if you want. So no was 526, that's the column. Always divide by the total number of participants in the study, 619. And that comes to 408.73. So their contribution, so if we look at the cross tabulation, males and no is 404 people, males, subtract 408 because that's what they expected. That's the, well, not that they expected that. That is the expected value based on the raw counts, 408.73. So those are the expected. Remember, it's always observed, subtract the expected, divided by the expected, and we get 5. All right, females. Okay, so we need to scroll up and down here to get the females. We'll do females that said yes to the study. So we need the row total. So 138 females in the study, and there's a total of 93. So that's going to be 138 females multiplied by 93 that said yes, 619 is going to be 20.73. So we'll keep going. Now we'll get their contribution to the chi-square. So observed, what did we see? Yes, females, 16, only 16. 16 subtract 20.73. The expected value divided by the expected value 2 equals. So observe, subtract. So just always remember that. Observe, subtract, expected, all squared. Don't forget to square the numerator. Divide by the expected. And one final one to go. One final category. We have females that answered no. We have a total of 138 females. Total that said no in the study was 526. So that will be 138 times 526 divided by 619. It's always 619. I think you see the pattern here. 27. So their contribution, total number of females that said no was 122. So 122. Another thing too to keep in mind, if you have calculated the expected value and it's really, really, really different from the observed, like I mean, it's out by a couple of hundred or something like that, then you probably have calculated the expected value incorrectly, or you've grabbed the wrong observed value. Notice that our observed and our expected values for each of these categories are similar, right? 77 versus 72.27, 404 versus 408, right? 16 versus 20, 122 versus 117, you know. So they're close in value, but if you had, say, 16 and 408, right? If you used 16 and 408 and you calculated 408, that's probably, there's a mismatch there. So be careful that you keep the categories and everything straight, but it's a good way to test and go, hey, maybe I must have done something wrong. They're just too different. So the chi-square observed value is the sum. So 0.310, that was the first category. Second category is 0.055. Third one is 1.079 plus 0.191. Grand total we end up with 1.635. So we want to compare. We want to keep that value in mind. So how many degrees of freedom are there then for this chi-square test? What do you think? Yeah, the numerator is always squared. So anyways, the numerator is always squared, but it's just a way to compare the observed value and the expected value. They need to be somewhat close. That's what I was trying to explain, is they can't be really wildly, you can't have an observed value that is really, really different in magnitude from an expected value. You probably want to go back and check. It's sort of an indication that something has gone wrong. No, not necessarily. It's just that the degrees of freedom is just, it dictates the shape, because the degrees of freedom is a number that goes into the function for the chi-square distribution that gives that shape. So that's all it is. And depending on the test, so you get different shapes for the chi-square, right? Depending on the degrees of freedom, you can get all different. I mean, it will still look similar like that, but maybe a little bit heavier in the tail, or less so on the less skewed. But it just, the degrees of freedom are just, they're just depending on which test you're doing. Yep. It's a good question because everyone thinks that the degrees of freedom is, some mysterious thing. All it is just a number that goes into the chi-square or the t distribution. It's just a number that goes into the formula to get those probabilities. All right, so I'll end the poll. So let's calculate. Let's see, most of you have said A. So it was R subtract 1 times C subtract 1. All right, some of you have put C and B. So what is R and what is C? Well, let's go back to our table. Now, I had calculated the totals just for convenience for us, but sometimes they're not given. The actual two-way table is just a 2 by 2, right? Because you don't count the two, you don't count the totals. So we have yes, no, that's under the influence answers, and male, female. So this is a 2 by 2. Oh, okay, let me just erase that. This is just a 2 by 2 table, right? Now we could have had 3 categories for gender or for driving under the influence. There could have been a yes, no, or do not wish to answer, right? There could have been a third category. Yes, I have been drinking. No, I haven't been drinking. There could have been a third one saying do not wish to disclose. Then that would be a 2 by 3, right? So you take the number of rows and subtract 1, and you take the number of columns and subtract 1. So we had a two rows and we had 2 columns. That's just going to be 1. So if you answered 1, that is correct. You were able to figure out what the don't include the titles, don't include the totals. So you can see here, so actually maybe I should not count that. So like you just really, this is really what we're doing here. Let me just get rid of this. Really what you want to do is check the data. Let me see if I can draw this better. It's really this, right? The answers, 2 by 2. And then if you're given the totals, great, you can just do what we did here. If you're not given the totals, then you need to calculate those rows and columns and get the totals and also the overall total, the capital N, right? So that's how you calculate the degrees of freedom. And then we can use that degrees of freedom. We can get our chi-square. So let's go back up and get our chi-square from our test. The chi-square critical value from the table, we'll use alpha, 0.05, with 1 degree of freedom. Straightforward to find that same column, right? We'll use 0.05. We'll use that row though instead. We want 1 degree of freedom this time, so it's just 3.8415. And let's see how they presented this to the judge, because they got 3.8415. This is the actual data set that they presented to the Supreme Court. And what you want to do is, okay, is the chi-square observed value greater than the critical value with a question mark? Because then if it is, it's in that it's going to be in that rejection region. If it is, it's going to be, remember this here is where the chi table value is, chi-square critical value. And if it's greater than that, it's in the rejection region. So is it 3.8415 is the critical value, is 1.631 in the critical region. Is it greater? The answer is no, right? It's not included. I'm going to stop the share of the poll. There's one more poll question coming up though in a minute. So no, so just as we suspected, right? We cannot reject. And this is why he won. This is why he won, partly why he won. So we cannot reject. So this here is what we want. They are independent. So gender and driving under the influence are independent. Doing one does not give you information about the other. So one final question then. How do you conclude? Based on the critical value and the observed value for this example 2, is there a relationship between gender and driving under the influence? Think about it. We already know that he won, right? The 18-year-old male that challenged the state and won. So we want to know what we want to understand what independent and dependent actually means. Be really careful in how we describe it. All right, good. All right, lots of you are in. Lock in your answer. It's just yes or no, right? All right, is there a relationship? And the answer is, most of you put no, and that is correct. No, there's no relationship between gender and driving under the influence, and that we were able to show and prove with the chi-square test of independence, because if there's no relationship, then they're independent, which is what we concluded, right? We accepted the null, we could not reject the null hypothesis, so we accept that they are independent. And that means that there was gender discrimination against males. This time it was against males because there's just not enough proof to show that males are more reckless or take more risk, according to that data. Okay, so the law was changed forever. If anyone has any questions, I'm just going to come back up here. If you're okay with these formulas, my scribbles here, if you have any questions, let me know. All right, anyways, we'll see you at the review for the final exam. I'm sure I'll have a review then, okay?